All right, today we're diving into Swift's modern concurrency system. We're going to see how it takes the absolute chaos of parallel programming and transforms it into something that's safe, structured, and honestly kind of simple to write.
You know, for the longest time, writing concurrent code in Swift felt like trying to walk through a minefield. You were wrestling with these super complex patterns like Grand Central Dispatch, which were powerful for sure, but they were also a nightmare to read and just filled with these sneaky, impossible-to-find bugs.
We went from this tangled mess of completion handlers, what everyone called callback hell or the pyramid of doom, and we moved to code that looks and reads like simple top-to-bottom logic, but it's got all this incredible concurrent power humming away underneath. I mean, the difference is just night and day.
And right at the heart of all that old chaos was this constant, lurking monster, the data race. This is one of the most infamous bugs in all of programming. It's what happens when multiple threads just trip all over each other, trying to use the same piece of data at the same time, and it leads to total mayhem.
So Swift's answer to all this chaos is this really powerful idea called structured concurrency. Think of it as a brand new blueprint for writing concurrent code that is safe and easy to understand by design, right from the very first line you write.
So the whole model is built around this idea of a task tree. It organizes every single piece of asynchronous work into a hierarchy, kind of like a family tree. Every bit of work you kick off, which we call a task, has a parent. And believe me, that structure is the key to everything.
And this structure isn't just for making things look neat, it actually defines these clear, unbreakable rules. A child task is scoped to its parent, which means it can never outlive it. It also automatically inherits important stuff, like its priority level. And the best part? The system manages this entire life cycle for you, which just prevents so many common bugs before they even happen.
Now this is the real payoff of that task tree. You get these incredibly important guarantees for free. A parent can't finish until all its children are done, so no more rogue tasks running in the background. If you cancel a parent, that cancellation just cascades all the way down to its children. And if one kid fails, the system automatically cleans up the whole related family of tasks. This is what safety by default looks like.
Okay, so how do we actually create these child tasks? Well, the simplest way is with our first building block, Async Let. This is your absolute go-to tool when you know you need to run a fixed number of things at the same time.
The way this works is so simple and elegant. You just use Async Let to kick off a child task, and your main code, the parent, just keeps right on going. It doesn't block. It's only when you actually need the result from that child task that you use the await keyword. That await becomes a suspension point, which cleverly frees up the thread to do other useful work until your result is ready.
Check this out. In this example, we kick off the download for image data and its metadata at the exact same time. Each one becomes its own child task. And the main function? It doesn't stop. It only pauses later when it calls try await because it finally needs to use those results. It's just simple, intuitive parallelism.
Okay, this brings up a fantastic question, right? What about cleanup? What happens if something goes wrong or the function just finishes before we even have a chance to await those results we kicked off?
And this is where the magic of the task tree comes right back in. Because Async Let creates a structured child task, its life is literally tied to its parent scope. If that function exits before the result is awaited, the system is smart enough to just automatically cancel that child task for you. No wasted work, no leaked resources, it just works.
So, Async Let is amazing for running work in parallel. But what about that data race problem we talked about at the beginning? How do we safely share and change data? Well, for that, we need our second building block, actors.
So let's go back to our sea of concurrency. I want you to think of an actor as a self-contained island. It holds its own state, its own data, and it's completely isolated from all the other concurrent tasks. Let's call them boats sailing by.
So a little more formally, an actor is a special type that basically acts as a gatekeeper for its own data. It creates this synchronized bubble around its properties and methods, and it guarantees that only one task can be on the island, changing its state at any given time.
To interact with an actor from the outside, you have to await your turn. When you do that, you're really sending a message to the actor's private mailbox. The actor then processes messages from its mailbox one at a time, in order. This system guarantees sequential access to its data, which completely eliminates data races by its very design. Okay, so we've looked at structured concurrency, and we've seen actors. Let's pull this all together. What is the actual, real-world payoff for us as developers?
Well, it's way more than just cleaner code. We get this new level of safety that's baked right into the language. The compiler actually helps us prevent data races. The system handles all the cleanup and error stuff automatically, and because Await suspends tasks instead of blocking threads, we totally avoid that classic thread explosion problem, where you just overwhelm the system. It's just a fundamentally safer and more efficient way to work.
I mean, the difference is just so stark. The new way isn't just shorter or, prettier. It is fundamentally clearer, safer, and less error-prone just by its nature. The amount of mental energy you have to spend is just massively reduced.
This new model really lets us shift our focus. We can finally move on from worrying about the low-level mechanics of locks and queues and just focus on describing what our code should do. It's a fundamental change in mindset. The question is no longer, how do I make this safe, but rather, what new possibilities does all this safety unlock?